So my name is Dr. Siddharth Pandey, and I am heading the newly established Center of Excellence in Astrobiology. Very good morning to everyone. Are we alone in this universe? Is life on Earth unique only to Earth, or can it exist? This is a question that does not only pertain to biology, and this is something that you will see from the backgrounds of the people here, that it's a question that transcends scientific disciplines. It also transcends art, it gets into culture, it gets into philosophy. So, including the ancient Indians, we've had civilizations across the world who have been pondering about whether their existence is rare or other worlds beyond. So what we will do today is we will go around having a short introduction from each of the panelists, and right after that we will start looking at, as you will notice that there are people from different countries and different regions, and they've been working in their own capacities in this field. So we will try to understand that in 2020, how do we proceed to collaborate and explore space together? It is no longer the Cold War era where people were just fighting against each other and trying to grab hold of space and put flags and say we are the first. I think we have moved beyond that, and India set a remarkable example when it was setting up the space agency. In fact, we were just talking before that we were the first nation to do space activities that were for socio-economic benefits, that were for the benefit of the common people. So after setting that example, I think India can very well work with other countries in exploring space from an international cooperation perspective. So what we will do is we'll very quickly have that introduction, we'll get into the discussions, and then we'll have some time for question and answers from the audience. So roughly we'll cover everything in one answer. Is that all right? So we'll take about 1 hour. Let's start with Dr. Jennifer Blank. She's from Blue Marble Space at NASA Ames Research Center. So tell us more about yourself, Jen.
Hi, I go by Jen. I'm Jen Blank, and Sid and I are actually both part of this astrobiology network that spans the globe and is headquartered in one of the NASA centers at NASA Ames. We're right in Silicon Valley, so we're surrounded by Google and Facebook and NVIDIA and other software developer companies, but we are all doing strange esoteric work. I studied English literature in school and geology, so I was always torn between having my nose in a book and being outside. And then I went to graduate school starting in oceanography to study the black smokers at the bottom of the oceans. But I had so many questions that we didn't have answers for. So that led me to start my PhD work over again at Caltech in Southern California, looking at the behavior of carbon gases and water in volcanoes and how they'd come up and come out of the volcanoes, how to help with eruptions and also ultimately provide food for life. These days, I'm an astrobiology research scientist at NASA Ames Research Center, where I work on the Mars rover Curiosity mission. Excuse me. And I'm one of the scientists associated with the first interplanetary laser, CAM, and we fired over 800,000 times on Mars. But on the side, I also these days look at places on Earth that could be good analogs for Mars. So working with Sid and this group here in India at Lonar Crater and Ladakh. And also I'm leading a project in California called the Braille Project that's essentially taking a robot into caves and looking for signs of life there. Because there are lots of caves on Mars, and personally, if I went to Mars, I'd want to go to a cave.
So I'm Michael. I am a microbiologist, so I did my first degree in evolutionary biology at York in the UK with a year in Aarhus in Denmark as part of an exchange scheme. And then I focused my research on microbiology, so the study of microscopic organisms, bacteria, and other single-celled life at the Norwich Research Park, which is just in the southeast of England. And having completed my doctorate there, I've now moved 2 hours to the west across the UK, and I'm now based in Milton Keynes, just north of London. I'm a part of the Astrobiology OU research group and team at the Open University, which is termed a University of the Air because they do a lot of distance-based learning courses and are the largest university in the UK based on student body and one of the largest in Europe. And my research focuses on trying to get an understanding of how microbes can survive under extreme environments, looking at some of these different analogues for extraterrestrial environments, such as salt flats from the Saharan Desert. And I was also lucky enough to work with some researchers from Catch University before coming here, visiting Bhuj and visiting the Great Rann of Kutch to try and study some of the salt crystals and the extreme microbes that are able to survive under those conditions. My research also involves simulation experiments, so taking microbes from Earth and exposing them to simulated Martian and other extraterrestrial conditions to try and understand, can they survive? Do they leave any trace or evidence of their existence? And what microbes don't? How can we use this information for future life detection missions? Thank you.
Hello, everybody. Can you hear me? So I'm Anna Lee Beattie. I'm from Mars Society Australia. I'm not a scientist, I'm an artist. So I'm interested in thinking about the role of art in small communities off Earth. What will happen when we go to the surfaces of planets or under the surfaces of planets like Mars? What role will art play, excuse me, in building new cultures in space? So to do that, I often go to places, extreme environments where art's not welcome at all, not necessary and not needed. So I work with scientists in places like, in 2016 I went on NASA Spaceward Bound with Jen, Sid and John, and we travelled to those high valleys of Ladakh, and I followed the science there. Less than a month later, I was in the desert on a 3-month space simulation. So we jogged hike again on the Mars 160, following the science return. So what I would do in that context is I'd find a role for myself that was art-based. So in those 2 instances, I became a field artist and followed the science and tested whether we could do field drawing in the spacesuit. Because we're in full simulation, wearing spacesuits the whole time. We only put the suits on when we went outside the habitat. So my role was to follow the science team and test in and out of simulation to see whether we could draw in the suit. So places like Bulby Mine, some of you might know the Bulby Mine underground dark matter laboratory, one of the deepest laboratories in the world, 1.2 kilometres under the ground. So a couple of years ago I went on an expedition there, and it's a dark mine, so drawing in the dark. So I followed 35 scientists down there in that mine who were looking at microbial samples of salt in the mine. Jen was there, and I drew everywhere I went. So I drew the miners, the tunnels, the darkness, the field science, just to see what art might be in those extreme conditions, in the dark, in 40 degrees. That was the kind of work I did there. So now I'm working with everyone here as part of the Amity team. This week we've just had 2 workshops at Amity University. One of them was an astrobiology workshop. So students from all different disciplines, science disciplines, came, and we talked about, habitability and where life might be found, what astrobiology is. And in that context, I did a drawing workshop. So we looked at rocks that you might find on Mars. And we did very detailed observational drawings of those rocks. And then on the weekend, we just had a popular science workshop. Any of you could have come to that workshop, and that was lots of fun. We met an astronaut online. Again, I did a drawing workshop with that mob. So very nice to meet you all. I'll pass over to John.
Hi, well, last but not least, it's me, John Clark. I'm a geologist, which means that I study rocks. I study the history of the planet. I study the history of other planets. I'm going to pursue being an astronomer, and they're right. I didn't have the mathematics to be an astronomer. And that was quite a crisis. It was one of probably the biggest personal crisis in terms of my career that I've ever had. And I thought, well, if I can't study the planets and the stars, I can study the star that I live on, the Earth. Because if you are on Mars and you look up at the night sky on Mars, the Earth is a star in the sky. And so I took up geology. I did a bit more biology at uni. I did philosophy. And since then, I have worked on 5 continents and in 3 oceans. I worked as a research geologist at universities. I have been a government geologist looking in groundwater, and I've been a company geologist looking for gold and copper and nickel in many parts of the world. So it's a pretty exciting career being a geologist. I can recommend it. Now I still work for the government in groundwater, but in my spare time I do astrogeology, which is a study of rocks on other worlds, and I'm involved in astrobiology, including being part of the team at Amity University. My main research interests are looking at Mars analogues, features that on Earth that resemble features on Mars that help us understand what's going on Mars. I'm also very interested in the challenge of how we are going to explore Mars, particularly when we have boots on the ground as astronauts. How long does it take to explore? How efficient are we? What's the best way to go about it? And so I've spent a lot of time, about 6 months in total, living in Mars simulations, and also many other months looking more broadly at analog environments. So it's an interesting career, and I think if any of you do end up doing planetary science, or indeed any science, when you get to being an older person like me, you can look back in your career and also say you've done some pretty amazing things over the years, and I'm very grateful to that opportunity.
Thanks, John. I'll also introduce myself. I have started my journey as an aerospace engineer, and I studied at Amity University before I took off. I was at IIT Bombay after that for a year, and went to the Netherlands, got a master's in space systems engineering. So I, since the age of 14, had always had an interest in space, and that has still stuck on for better or for worse. In fact, it was Kalpana Chawla's incident that really got me thinking about the fact that this is one career that requires a lot of dedication and determination, and if I had to be doing all of those hard math problems and solving those physics equations, it had to be something that would keep me interested. So I think if I'm not interested in the problem, I don't want to solve it. So that is one of the reasons that aerospace stood out. And in India, as you will see, you first get into an aerospace engineering program, which is general. You cover different aspects of flight, aerodynamics, propulsion. And then for my specialization, I started studying space environments and how do you design vehicles that operate in those space environments. I got an opportunity to go to NASA Ames Research Center. So I was there as an intern, and then that project rolled over, and I was able to take up a research position there, which I held for about 1.5 years. And that's where I got initiated into the field of astrobiology. And NASA Ames Research Center is one of the very important centers where many early astrobiologists worked in kind of establishing it as a field. It was initially called exobiology and then astrobiology. And from there, I moved to Australia to get a PhD because I decided that as an engineer, my role was very limited. So I had to get into the research aspect of things. And while I was in Australia, I met Dr. Jonathan Clark and EVT with the Mars Society Australia. We were able to do several local expeditions within Australia. We went to New Zealand. We worked in Rotorua, which is a site where you have these hot springs in the North Island of New Zealand. And I met Jen there as well. And the concept of Spaceship Bound was introduced to me, which is a NASA program. It's an education program that NASA Ames has started. And in 2016, we brought NASA Spaceship Bound to India. So I was part of the team under the guidance of John. We identified Ladakh as a region which had immense potential from an astrobiology perspective, because Ladakh is an early Mars analog. So some of the high altitude, very high altitude, low oxygen, UV radiation exposed environments actually support some very extreme forms of life, microbial life, and very diverse sites. So you have hot springs, high altitude hot springs, where you have all of these liquids, hot liquids that are gushing out from underneath and coming out to the surface. So you don't have to drill down to see them. This is just naturally coming out, and that's why hot springs are very interesting to understand. The ancient or the history of rock and fluid interactions that have taken place, and because of the energy in that environment, the kind of microorganisms that are actually living in close to boiling, temperatures. You also have glacial sites, permafrost, permanently covered ice. So, some of you who have been to Ladakh, how many of you, by show of hands, have been to Ladakh? No one.
One person.
Yes.
One person there.
Two people.
Student down
Be
there.
confident, yes.
Hands up, student.
How many of you been to Ladakh?
Two.
Mr. Srinivas Lakshman in the audience, he was so with us in our expedition, and perhaps you can all talk to him about his experiences. But I would suggest the next holiday you plan, you should go to Ladakh. There are now direct flights from Mumbai, but go there and visit that place in a sustainable manner. One problem that now we are facing with all these sites is people leave behind their litter and their trash, and they see nice environments, they take photographs and come back. But I would encourage all of you to read more about Ladakh. We've actually had a research paper that came out. We've also done some articles which talk about the scientific importance of Ladakh. And from a Mars exploration perspective, it is similar to what early Mars was like when there was water on the surface. So anyways, I digress from my introduction. So we did the first astrobiology international expedition in 2016, and after I finished my PhD, I came back and I got an opportunity to join Amity University, and we established this Center of Excellence. And the goal for us right now is to scope out these regions in India which can help us solve some of these astrobiology questions. So Lonar Crater, how many of you are familiar with Lonar Crater? Just raise your hand properly so I can see you. So not many. So Lonar Crater is a site where the age of so it is a site where a meteorite impacted a place close to Aurangabad, 3 hours away from Aurangabad, within the Deccan Traps, and it created a crater site. All of you are familiar what a crater is? So it is. Can you hear me? Okay. So this crater is basically a site which has formed in a very hard kind of rock, which is known as basalt. And because of this hard rock, it is not like a soft rock which weathers out and erodes over time. So the age of the crater is still, I think, under discussion. It hasn't been confirmed. Some people think it's 500,000 years. Some think it's about 50,000 years. But a long, long time ago, this impact took place, and because of that energy, we had this crater formed. And over time, there is a lake in the center of the crater. There is a stream that is feeding into that crater, and it is important to us because there is a rover, a NASA rover, that is going to a crater on Mars. And that crater, although it is much larger, it is very similar to our crater here in India, Lonar Crater. And there are only 2 or 3 other basalt craters that we have on our planet, and Lonar is one of the easily accessible ones that we can get to and study. And more importantly, because of this stream that is flowing and depositing sediments, this delta region, it is important from an astrobiology perspective, because when this rover that is going to Mars, it lands inside this crater, it is landing close to an ancient delta, as it has been confirmed that there was liquid water flowing on the surface of Mars a long, long time ago. It would have deposited organics from the vicinity of that crater into that place. So it is one of the best places where you can actually find proof of ancient traces of perhaps life. So that is why the NASA 2020 mission, it's an astrobiology mission, it is going there to do that. And one place where we can test our equipments, we can do experiments, is Lonar Crater. So that is one site that we have identified. So the objective of our center is to preserve, promote, and at the same time collaborate with experts from around the world, closely with the Indian government as well as people on the outside, to explore this crater from an astrobiology perspective. And we're also doing a lot of outreach work, science and education outreach work. So that is my very long introduction. but I also have brought out and highlighted some of the sites, so I hope that will save some speaking time. But I think with this discussion, what would be really good to understand is in the near future, in the next 10 years, what are some ways in which we can perhaps engage scientists? I think one thing which astrobiology brings out is the importance of both interdisciplinary researchers as well as researchers from different regions that tend to work together. So what are some of our, I think, near-term goals in the next few years that we can set? Maybe we can start with John, because from an Australian perspective, what do you think are some of the key areas of our collaboration? Let's establish those first.
So it's a good example or a good analogue, a test case to compare against what we know about early Mars, to understand how the processes worked, how life might have existed there. We talked about Lunar Crater. It's one of the very, very few craters on Earth that's into this rock called basalt, which is very common throughout the solar system. It's quite common on Earth, but for one reason or the other, very few impact craters have developed in that. And it's got a salt lake in it, which may well be similar to salt lakes that we see once existed in many Martian craters. So we've got to really choose very carefully where we can spend our time that is most relevant to where we want to look for ancient life on Mars, or evidence for ancient life on Mars, perhaps even modern life on Mars, but also places that would help us understand the history of the planet. There's a whole planet to choose from. Mars is a small planet, half the size of Earth, but it has no ocean. So the surface area is the same as Earth. The land area is the same as Earth. So if you had the whole Earth to choose from, and you only had 2 or 3 places to go to, where would you go? Would you go to Antarctica? Would you go to Lake Victoria in Africa? Would you come to Mumbai? Would you go to somewhere in Utah in America, or to Scotland? It's quite hard if you wanted to characterize Earth and you only had 2 or 3 places to choose from. Where would you go? And when we look at Mars, we've got a similar choice, a very hard choice. So we want to choose the best places. And this is why landing site selection for both robotic missions and ultimately crewed missions is a very challenging task. So we want to look at sites in India that can help us make that decision. Lunar Crater is one, Ladakh is another. There may be other sites that we don't know yet. But we've got to choose carefully. And it's great challenge, great fun. You know, science is fun. I think we've all had fun in our careers. And if you take up science as a career, or you take up science education, or science art, or science journalism, you know, you'll have fun too.
Good, John, thanks. I'd just like to add a little bit to that, and that is, first of all, what is astrobiology? We haven't really mentioned that. Astrobiology is this very big umbrella term that can mean just about anything. So traditionally we think of it as the search for life in the universe. And that might be actual life, but it also might be just the search for the elements of life, like carbon, for example, coming out of stars. How rapidly do stars burn to produce carbon that can be, or the primary elements of life? Carbon, hydrogen, oxygen, phosphorus, and sulfur, and nitrogen. Another thing with astronomy, the astro part, is looking for molecules in space that could have contributed to that sort of prebiotic soup that might have led to life. Molecules such as amino acids that we've now seen in the interstellar medium. Or I just learned this morning there's a research program in India looking at or searching for chiral or types of sugar molecules or sugar acids in the interstellar medium also that could have possibly led to our DNA on Earth. So that's all pretty exciting. But coming back down to the planetary scale, one of our big question of interest is where to look for life in our solar system, because that's probably more accessible in our lifetime. So John's mentioned Mars and mentioned places on Earth that can help us prepare for searching for life on Mars or searching for life on icy moons of other planets further out. And NASA has a mission to Mars that's launching this summer, and so does ESA. And then they're both robots that are essentially field geologists. And for the first time since the 1970s, these rovers will be equipped with instruments that could detect organic molecules and maybe changes in organic molecules that if it's alive, it might be able to detect it that way. So that's pretty exciting. But in terms of how students can get involved and how researchers from other countries can get involved with these European and NASA missions, there are ways. After about the first 3 months of a mission, all of the data collected in these missions, at least from NASA, are put in a public database. So they're accessible all around the world. And so it's all about using creative tools, whether they're software tools or just creative ideas on how to make signal out of the sort of the noise of these massively complex data sets. And I think as we share these data sets and have more and more data sets about Earth and about Mars and about our moon and about the icy worlds beyond, this will, and also with the software tools available, I think that's really going to democratize our study of this of our solar system, and that's going to be really exciting to see what researchers at universities and also researchers who are citizen scientists who might just be doing something on the weekend or set up some kind of a bot that will be helped to data mine and look for patterns in these massive data sets. I think it's going to really democratize space and our search for life in the solar system. Anyone else have anything to add to that? Oh, yeah, please. You have one too. But go ahead. It's such a luxury to have each have our own mic, because usually you have to share.
Okay, fantastic. Can you all hear me? Okay, fantastic. I think building on what you've both said, and just with regards to, in the short term, how do the astrobiology missions that are planned go forward, and something that's already been touched on is the interdisciplinary approach. I mean, if you look at just us on this panel, it's 5 very different approaches for, say, if we get water samples from Lunar Crater or take sediment cores from across it and try and understand that. I think we would take 5 very different but equally very valid approaches, and I think the idea of recruiting from different specialties and
that's true. You're really the only one who's studying life. Sid's looking at instrumentation to help detect life. John's studying rock records of life. Annalie's studying how to characterize and describe life and communicate how we define life. And I actually study the food from rocks and chemistry for life. So you're really the only life person here. But we're all astrobiologists, so that's cool.
And I think that they're looking at it from every single one of those perspectives and increasing perspectives as the work and the research aims continue to grow. I think that elevates the research to its highest possible level. Like, we don't want to send out 10 separate missions to the same place to try and answer slightly different versions of the same question. We want to really try and dig deep and get as much information from these incredibly valuable sites as possible. And I think the interdisciplinary approach is essential to that, so bringing in experts and different perspectives and different opinions. And I think that you've been able to lay a lot of the groundwork for that with the establishment of the centre, but also the workshop that you organised the past week. That we've seen a collective of roughly 50 individuals over the 2 workshops, all coming from different perspectives, a younger perspective than everyone on the panel. And I think that diversity of specialties and diversity of ideas is something that's the key to really driving the science.
Also, some of these questions, although fundamental, are hard questions. Defining life. We had an activity where we had divided the entire team into groups, and we were giving them images of objects, microscopic images, images of microscopic objects, and they had to decide whether this is a living object or a non-living object. And by the end of it, there was a very intense deliberation between the people, and for a very good reason, because some of the images were controversial. Even right now, people are publishing whether they have identified a particular strain and that is bacteria, or if it is not bacteria, whether virus is classified as, like not many people know that by actual definition, a virus is not a living thing. So it again boils down to how do you define something that is living? What does it really require for it to be, given that status, if you may, of it being living or non-living?
And if we can't even agree here on Earth, how are we going to agree on whether or not we detect life?
Yes.
With our instruments that go to other places,
yes.
Unless that life walks up and waves at our video camera.
Yes, exactly. And it also brings up this question of missions. So we have a US mission going, European mission, hopefully a Chinese mission at some point to Mars, and an Indian mission is also in planning. They are reconsidering perhaps flying a roving mission rather than just doing an orbiter-based mission. So with all these science groups, and there might be some scientists who are experts and perhaps overlapping between the different teams, but then again the approach. So culturally, how does a particular culture affect the definition of an experiment that is about to be flown? Where does it draw the limitations that, okay, we are just going to do this and that's it, and we have determined whether it is life or it is not life, whether a different culture might be a little more flexible to that and might leave it open, and they're not explicitly saying that, I've met people who don't want to call instruments life detection instruments. They feel that even saying that you're going to detect life is controversial enough. They're going there to look for biosignatures, biological signatures. So things that are either a byproduct of life or a precursor to life, but not life by themselves. So these are very interesting times where we are answering these, or attempting to answer these very fundamental questions, but then the cultural nuances are coming in. There's also the aspect of planetary protection. And it's interesting to see how different countries are observing, abiding by the protocol of planetary protection. Perhaps I should define what is planetary protection.
Right, because when I first heard the term planetary protection, I thought it meant protecting us from
aliens,
or from viruses or microbes that come from outer space. But
Yes.
it's actually protecting the places off-world from us.
Yeah.
So.
Well, it both ways. So forward contamination and backward. So in a way, you were right. So yeah.
Okay, but the most of the emphasis is on
Is
making
on-
up sort of essentially some regulations
That's
to
right.
try to protect Mars or protect the moon from
Yeah.
contamination by us.
By us, exactly. And some groups will say that, it's already been contaminated, so should we really bother about it? Whereas the others might feel that there are some parts, which you can go ahead and do all of your science, so we won't touch those. So we'll ensure there's planetary protection in those sites, which are important from a scientific perspective. But there are other places where we know that there cannot be any life, so we shouldn't go there. So how do you draw those lines, and how do you abide by them? And there isn't a international treaty that regulates planetary protection. Every space agency has their own planetary protection office. I'm not sure if ISRO has one yet, a planetary protection office.
They must, right? And this proto treaty is evolving.
Yes.
But it needs, as more and more countries migrate into space
Yeah.
or become spacefaring,
Exactly.
we need it. And right now, the initial drafts are based on the treaty for Antarctica, but there's still a lot of lack
Exactly.
of agreement.
Yeah. So Antarctica is a very good example to understand how countries work in terrains that are not nationally governed, but they're open terrains. Sorry, John.
You touched on something very interesting there
Yeah.
about what is life. Are viruses alive?
Yeah.
Probably not. And one of the problems in astrobiology, when we're sending spacecraft out to Mars or to Europa or anywhere else, is would we actually recognize life, or particularly would we recognize fossil life there? Because we can only look for life as we know it. I mean, we can also imagine some strange life, but that would be a bit harder to detect. But there also may be life out there that we can't imagine. There's a story about late one night, a police officer's walking down the street, and she sees this drunk man scrabbling on the ground around a lamppost. And she goes up to him and says, "Sir, can I help you?" And he says, "Oh, I'm looking for my car keys. I've lost them." And she said, "Sir, where is your car?" And he said, "Over there in that dark corner." And then she asked him, "Well, why are you looking here around the lamppost?" And she says, "I can't see over there. I can only see where the lamppost is." So perhaps when we look for life on Mars or Europa or wherever else, there's a danger that by only focusing on the life we can understand, we may be like that drunk man looking around a lamppost for his keys, when in fact the keys are over where he dropped them near the car. And we have to be aware of these traps that we can paint ourselves into when we design our missions, design our instruments.
And Annalie, I'd like to ask you, how can we bring the essence of all of this work to the people, and you've had experience doing that in different capacities and different environments. You've been working locally with communities that live in these and work in these extreme environments. From a large-scale perspective, what should be the push, to ensure? How can we take the people along? Basically, I think that's what I'm trying to ask you. What would be the? It's a big, large, open-ended question. But your thoughts on that?
How can we take the people?
How can we take the people along?
How can we situate the science in
Yes.
in the community?
Yes.
So, I don't know. As an artist, I do a lot of project-based work in communities. So working with people to understand, what their community is and what stories they bring to the table. When we think about science, it's a really bad idea, I think, for us to just go into a place and do the science and walk out without understanding the context for where we really are. So, for example, at Lona Crater, maybe I can just give an example.
Absolutely.
I'm thinking about a project, and if any of you want to help me with this, you'd be most welcome to email me. So the last time I went to Lona, I visited the primary school next to the crater. Everyone knew what the crater was, and a lot of children in that school, their families had been born around that crater. They lived there for centuries. So I talked to the headmistress. I said, what can we do to understand the stories that children bring? And how do we understand the geology of the crater? And how do we highlight the significance of Lona Crater for children in the area? And so we came up with a bit of a plan that we'd use the local kilns and the local clay to make craters, and we'd make bowl craters so that they were functional objects as much as they are decorative objects. And when we made those craters, we would identify the delta and the ejecta and the gullies, and we would use the glazes as the water coming into the Lona Lake. So we thought maybe we could situate the science in that way. So I guess my answer is for artists to work with scientists in communities, we think through our hands, and we start locally with local knowledge, and we always think about who our audience is and how we can highlight the goals of the science through making things. So targeting maybe underrepresented groups in communities is a good way to start and understand where you are. When you go to a place, it's not just the geology is the context for the biology, it's actually the people that already live there.
Mm-hmm.
It's a really important part of the story.
Mm-hmm. And are there any distinct challenges that are faced from region to region?
No, I don't think so. Actually, I think quite often when you're making, I think that's the good thing about making art. I think once you start to make something, then you think with your hands. So maybe there are challenges in materials and access, and like when we went to Ladakh, we were working in the schools there, and access and materials, they were a big problem.
Yeah.
But I think that's the kind of, for me, that's the really good thing about being an artist in space sciences, that once you start to make things and you don't really need to talk about it too much,
Yeah.
you can think with your hands and do it that way.
Yeah. And sorry, before you
I
add.
was just going to say, and also one thing I think art brings to science is the use of observation, using observation skills or developing those to both be able to see new features and to then articulate them or describe them. And that actually is an important tool for life, just for living in society, and whether it's looking at trying to pay attention to the people you're talking with, so you can see signs that might be body language indications of interest or not, or other things. And I think these are essentially tools that we might not acknowledge or understand right away how their value to science and the scientific method, but that actually are really critical.
Mm-hmm.
So it's really interesting in the art world, like sound is the new vision. So, it's a lot of sound art. Everyone's into sound vision, sort of like 20th century, and we've all got too many objects and we don't need any more. But it's been interesting for me working in this field that observation is that key skill set, because when you go to Mars and you're wearing a spacesuit, you're not going to be able to pick up, the geologist is not going to be able to pick up the rock and lick it or sharpen your pencil and blow the shape.
So the question was, to paraphrase, and please correct me if I'm wrong, why a virus is not considered living. So the definition of life, if you get 10 biologists in a room, they would come up with 10 slight variations on the definition. But one of the requirements that's considered for a thing to be living is that it can replicate on its own. It can replicate without another species or another organism being present. So rabbits, plants, microbes can divide. Viruses only replicate by infiltrating other cells, so human cells, bacteria. They inject their DNA in, they take over. Lots of copies of the virus burst out, but if you have a viral particle on its own or a flask full of virus, it wouldn't, the number, if they didn't decay, would stay exactly the same. So not being able to replicate on their own is one of the key parameters. It's very controversial, but that's why viruses still aren't considered.
Do you have a definition yourself? Are you in the viruses are alive camp?
My name is Dr. Jayaraman. I'm a professional nuclear scientist. Years ago, I remember that the C2H5OH was the most superabundant element in the stellar molecules. Currently, which molecule has the highest superabundance in stellar species? From C2H2 alcohol, where are we now?
In the interstellar medium, so it really depends on where we point. So in the interstellar medium, but it still favors the smaller elements. So hydrogen is the most abundant, right? And then when we start to see carbon, we see mostly CH molecules or CN molecules of this sort. So those are by far the most abundant. And when we look into the sky, we're looking at the whole integrated column, right, of the entire sky. So if we point to the regions with dust, then we start to see higher order hydrocarbons. So things with more carbon molecules, or more carbon atoms in a single molecule. But it's still fundamentally hydrogen.
Hi, thank you for your thoughts. Kashish Patgani from the Observer Research Foundation. Let me just preface my question with our intent to partner for this event. So ORF is a foreign policy think tank. So basically, Jonathan, we are the guys who are not good at maths. So we got into social sciences and international relations. When I was speaking to Siddharth about this event earlier, when we were thinking about this, our idea was that my community and my fraternity is mostly guilty of over-securitizing the global commons of space. Can I have another mic? It's working.
I hope they got your idea.
So, this doesn't work too?
No, it does.
Yeah.
It does.
It's working.
It's working. You can go ahead.
Thank you. So like I was saying, my fraternity is mostly guilty of over-securitizing the global commons of space. So relative to the global commons on Earth, whether it is the airspace or the oceans, the space and exploration of space enjoys a certain degree of insulation from policy turbulences when it comes to interstate relations. And I believe that's mostly because of the strong institutional ties that you guys maintain with foreign countries, right? Do you think that an odd consensus that countries have with respect to space exploration will break down at some point, or do you think it will remain to be that novel one space that continues to have a positive sum game and not a zero-sum game? Thanks.
Pardon me. If I may have a go at that, of course, a very famous scientist, I don't know who, said prediction is difficult, especially where the future is concerned. I'd like to think that this cooperation will continue. I was talking to a space lawyer in Australia, and he pointed out, it was at a conference, and he pointed out that the Outer Space Treaty has been in force for over 50 years, and there's never been a court case in connection with it, because although there has been conflict between different parties, they've always been able to resolve those conflicts under the principles of the Outer Space Treaty without actually taking it to court. So I'm moderately optimistic that this will continue, because people realize that space, you can't really hold territory. You know, you can have, a country can have its airspace overhead, but you can't extend that to infinity, otherwise you'd be every day claim 3/4 of the universe. So I'm optimistic. But of course, people can be very stupid sometimes.
Or do you think that convergence is because of the common fear of the unknown or the known unknown, whichever is scarier?
Well, hopefully not fear, but an awareness. I think when people contemplate the universe, even the solar system, or even just Earth orbit, they realize we're dealing with something where excessive selfishness or excessive nationalism isn't going to work. And I'm an optimist about the future. I'm a possibilist about the future. I think there are good possibilities, and I hope that people actually remember that and keep working towards that.
Yeah. We'll take another question.
Yeah, I'm Rupa Roy, and most of the children here, I had them, so they belong to me. So, from what I understand is that we have been unable to define what is life. And we also are not sure, as Dr. Jonathan said, about how life would evolve elsewhere. So if we do come across life somewhere else, would we know that this is life?
That's a brilliant question, and it underpins so much of the research in the field of how would we know life if we saw it, like Jen was saying. If an alien walked across the screen and it waved, well, we presume that was life. But I've read science fiction books where there's robots on planets that aliens sent out, and then other people meet them and they think, oh, this is the living thing on this planet because it can move and it can interact with us. So one of the ideas is that it's possible that life didn't arise on Earth, it arose on Mars, and then it was seeded onto Earth. So the presumption that it would be similar, or it would have the same, a common ancestor between life. So maybe our definition of life, our working loose definition, that things can grow, metabolize, reproduce, and evolve, would hold true for a Martian microbe if there was one. But if there was something with a completely different chemistry, or arose through completely different chemical processes, I think that would have major implications for the definition of life, but all of the sciences and philosophy. That if there were something like based on a different element, or didn't evolve, or didn't reproduce, then that would have major ramifications for how we understand life and living organisms.
And I'd like to just add a practical note to that, and that is, you're right, we all of our searches for life in our solar system essentially are driven by how we understand life based on our perspective here on Earth. And that makes sense in terms of defining a mission, defining objectives, defining what we need to search for life as we know it. It's very hard to define a mission to search for life as we don't know it yet. And that would be a very hard sell for the government agencies that fund us. Hey, we want to go to this planet and look around and maybe we'll find life as we don't know it. That said, it's a wonderful thought exercise, and I think it lends itself to contributions from people of many disciplines and backgrounds to try to imagine other things that could constitute life. For example, NASA has just recently announced a mission to Saturn's moon, Titan. So we're going to send a helicopter to Titan and hop around on the surface of this moon that's full of hydrocarbons and liquid antifreeze lakes. Now, we can't really imagine a water-based life that could live there, at least not on the surface, but who knows what we'll find. And so the mission is not, let's go look for life on Titan, but let's go characterize that really unusual chemical environment that's perhaps the most different from life as we know it, or rather Earth as we know it, and see what we find. So not looking for life, but looking for other regions of exotic interest maybe.
Yeah. I have one question, because since we have geologists here, we were talking about this Lunar Lake. So sir, do we have any idea about why pH level is so high in Lunar Lake?
Lunar crater is in basalt, as we have mentioned. And there's rainfall, the rain percolates down through cracks in the rock, and it reacts with the minerals. And generally rainwater all over the world, when it interacts with basaltic rocks, becomes quite alkaline. There are also salts that will be in the rain. Rain when it falls has traces of sea salt in it, and that adds to that. There may well be microbial processes going on that produce the very high pH waters, but in a number of parts around the world there are these very high pH lakes. There's several in Africa, for example. There are some in North America. Some in Ladakh or Sokar, where we want to do further work there, is also a very alkaline lake. So it's a well-known pathway for groundwater to move in as it interacts with rocks and gets concentrated by evaporation.
Why does everybody look for water before, or any form of water before they check if life exists? Because all they need for life to exist is a liquid which is not very reactive and is not too thick. Why do we only search for water? Why not any other liquids that follow those conditions?
Why do we look for water? Well, the simplest reason is that we think that life requires water. And water actually is very reactive. You know, it's a polar molecule. It means that water is 2 hydrogens plus 1 oxygen. The oxygen attracts, it's negatively charged, so it attracts positively charged ions. And the hydrogens are just the opposite, so they attract to negatively charged ions or molecules. And so that has actually become very important, as far as I understand it, in just the whole makeup of living things, right? This sort of gradient of electric charge helps set up, helps inspire reactions in life as we know it. So looking for water, though, since we think water is a key ingredient of life everywhere on Earth, looking for water might be the first clue as to where there could be something like an ingredient for life. Now, doesn't mean there's life there. It's just that we have instruments on Earth that can detect water. And so that's sort of the first, the minimum point is to find where else could we have liquid water or water on Earth that could support life as we know it. But you're absolutely right. There are people who suggest that maybe there could be forms of life in this super, super cold antifreeze on Titan, for example. But maybe it would be a carbon-only life and not a water life. And sort of a carbon liquid has very different reactivity. It's much less ion or much less polarized than water. So our sort of creations of how we can envision a life that lives and is made of antifreeze are really just sort of fiction at this point because we don't have any examples on Earth. So we really, again, go back to we're searching for things based on our perspective here on Earth.
So thank you for asking that. Another reason, I think Jen has given some fantastic reasons why water almost seems to be unique amongst molecules that when they're liquid, that have properties that support life. But there's also another reason. Water is very common in the solar system. So there's a lot of ice on Mars, for example. There's a lot of liquid water here now. There's a lot of ice on Mars. We know that in the past there was a lot of liquid water there. The ice was warmer perhaps, and the water was able to flow as rivers and lakes. Many of the moons in the solar system are essentially made of ice. And we know that at least some of them, perhaps most of them, have a layer of liquid water under them. And when we look further out into the universe, water is a very common molecule throughout much of the observable universe. So providing that water can become liquid, it doesn't stay as a gas or as a solid, as ice, there is a potential for life as we understand it to occur there. So yes, there's these weird liquids that we might find in Titan and other places, but they are perhaps less common than liquid water. Perhaps. Our ideas may change. Maybe you will research this question in your later career and perhaps find a better answer than what we have at the moment.
You said you researched for life on Mars, right? So can you please elaborate more about your research?
Well, a few of us are actually looking at that question. At the moment, that sort of research is focused on finding places where life could exist. As Jennifer said, we look for habitable environments. So we look at places like Gusev Crater, where the Spirit rover was roaming. We look at places like Gale Crater, where the Curiosity rover is now. Where Jezero Crater, where the 2020 rover is going.
Also the European rover, the Rosalind Franklin rover, will be going in an ancient river valley. All these places had, at one time in the past, liquid water, and in some places energy sources like hot springs, and they're places where organic molecules could be trapped. And we've found that these environments were habitable, the ones we've been to. So back in the early 21st century, the rovers like Spirit and Opportunity were sent with the principle of follow the water, look where the water was, see if it's habitable. That question we've answered. We've found these formerly wet environments that would have been habitable. So now we're narrowing it down. Where in a big crater that's 100 kilometers across, where might we find actual evidence of life? So that's where the research is, narrowing down the target so we can send our spacecraft to better places. And that becomes an engineering problem. The first successful landers on Mars, the Viking landers, would only land in sort of a big ellipse that was over 100 kilometers long. So they had to choose somewhere really, really boring to land. Because if it wasn't boring over that area, it could have landed on a cliff and bounced down the cliff and be destroyed, or on a mountain peak, or in a deep hole and not be able to do any work because it was just surrounded by the crater wall. So as our targeting becomes more sophisticated, so must our spacecraft become more sophisticated. So the 2020 rover, I think, will be landing in an area less than 10 kilometers across. I mean, that's still pretty big, right? But it's much better. It can land much closer to interesting sites. It's still got to land somewhere flat and boring, but it can then drive to somewhere that's more interesting. Remember that when you're designing a space mission on a landing site, the engineers always win. They'll always go somewhere boring, but once it's landed, then the scientists get their chance.
I just want to add one thing to answer, or to address the question. That is, tell us more about your geology on Mars. The cool thing about geology and about studying rocks is that rocks last for a long time, and rocks record a history in their chemistry and in their textures of the conditions of the formation. So how cool is that? So as Annalie, actually one of my favorite comments from the drawing class we had this weekend was that someone said, I never knew that rocks could be so fun. Because in drawing a rock, the person or they all had to look at that rock really carefully. And you can see, heck, is a pebble in the rock, is it rounded? Well, how did it get rounded? Well, it probably got rounded by being washed down a river stream and being abraded and going from an angular rock to a rounded rock. Likewise, we can understand, we can rather model the water that would have been present when that rock crystallized or was formed. And so one thing, even though Mars' surface doesn't have liquid oceans or streams today, by looking at that rock chemistry, we can predict or calculate the composition of the water. And so one of the coolest that was there when that rock was made. So one of the coolest discoveries of the Curiosity rover was that the water that we believe was present when those rocks were the rocks were formed was actually very mild water that could support life on Earth and that would have been drinkable for all of us. So it would have been a very healthy, natural water. So by having the objective, an objective is something you can achieve. By having the objective of follow the water or determine the habitability, we were able to do that within the first 6 months of the Curiosity rover mission.
Every rock tells a story. And you've all seen pictures, we mentioned the dark, you look at a picture of the mountains of the dark and you see all these layers of rock, yeah? Every one of those layers is a page in the history of our planet. And Mars is the same. Mars has multiple layers. And we can use the language of rocks that we learn here by drawing them, by studying them in the field, by looking at them under the microscope, to start reading the story of Mars. Because the language of rocks is the same all over the universe.
Next mission, what I've been reading about it. I mean, 2024, the ESA mission is going on, bringing it back. Could you like to throw some light on it?
Oh, so the question was about the Mars 2020 mission is going to have a complicated piece, which is about Mars sample return. So yes, even after the mission was announced, there's always been the interest of bringing samples back to Earth, because we know from the moon, from the lunar program, that we can learn so much more in our laboratories on Earth than we can by sending a robot to the planet. It's just very expensive to send a rover back, and it's very difficult to collect the samples and put them in a container. So that's one piece of the Mars 2020 rover that has been developed, which is to actually take samples and put them in small containers that are inside the rover, and then at some point that rover will be able to just eject a little pile of these containers with different samples that the rover has picked up along the terrain. So essentially it will make a little cairn of material for a future robot to come and collect. So it is very complicated because by having a sample return, this rover will not be able to return to Earth. That means another mission will have to go to the same place to collect those samples, right? So that means we're kind of limited in we won't be able to look at a new spot on Mars. We'll have to go back to where we've already been. And then also, it might take 5 or 10 or more years to get back there. So we have to put them in a container where they won't change in chemistry. So it is a complicated engineering feat.
And just to add a little bit of the engineering challenges to that, as you all are aware that we had sent astronauts to the surface of the moon, they landed, picked up samples and brought them back. But why do you think it's harder with Mars? Because it's further away, right? So you need to carry more fuel to go there. And it becomes a more expensive, more complicated mission as well. The other thing is landing on the surface of Mars is very different as compared to landing on the moon. When you're approaching Mars, you're going at a very high velocity, so you have to slow down, and then you have to enter the atmosphere, and then use some of that atmosphere to slow yourselves down. And in a very complicated mechanism, there are several ways, different missions have done that, which you soft land on the surface of the planet. And that entire exercise from Earth to Mars uses up a lot of resources, energy, fuel. So far there hasn't been a mission where they've carried enough fuel where they can use the same landed spacecraft to again launch and go into space, into Mars orbit, and then return back. So therefore there are talks of rather than having the entire mission in one spacecraft, distributed into several different spacecraft. So one mission goes there, lands, collects the samples, and then a second mission goes there, which uses that space for ascent vehicle. So it's not going to be doing any roving or anything. It's going to collect the samples from the first mission, and then it is going to launch as an ascent vehicle back into Mars orbit, and then while it is there, rendezvous with an existing orbiter mission, and then bring it back to Earth. So it's a very complicated mechanism. Complicated because it requires more energy, also more technology to be able to do that. So these are some of the challenges that are faced when we are doing these missions.
Mars 2020 has got a new instrument, apart from the sky crane, which will ensure that 7 minutes of terror becomes 7 minutes of joy.
Yeah, we'll take last question. The last question.
Thank you for that interesting panel discussion. My question is open to all panelists. I would like you to elaborate on what is happening of a collaborative effort across the globe where people are contributing their computing power, the processing power, all network computers, and specifically what is happening at SETI, SETI. So across the world, what's happening with everyone sort of pitching in?
SETI.
Okay, first of all, talk about what's happening with SETI. Does everyone know what SETI stands for?
Yeah.
The search for extraterrestrial intelligence. So not microbial life, but intelligent life. So there is an institute called the SETI Institute, and they've been listening for signs of intelligent life in the universe, and listening mostly by having big radio astronomy arrays to listen for radio signals. And in terms of international collaboration, well, when they are listening, they only are able to listen to a small portion or small area in the sky. So by having arrays around the world and having arrays that are citizen SETI programs, so essentially radios and small telescopes that are not being used, have them work at night or something, we can listen to more parts of the sky. And that's the idea. So there is a program called SETI at Home that helps process the signals that are coming in from the radio telescopes. And there is an effort to establish links with smaller and smaller telescopes that are more affordable around the globe to help increase the area of listening. So that's the one question. And I'm sorry, what was the next? And maybe I'll hand it off to another panelist.
Related, I said, what is happening with the students and other
Yeah.
communities across the
Study at Home is managed at UC Berkeley right now, but it's ongoing. And there is a big array in Central California that has, I think 105 of these small, they're 3-meter diameter arrays, and there are plans to put them in other parts of the globe.
Okay, thank you. I'll request all of you to put your hands together for our panelists.